So we introduce a layout for how to put the data on the store device and how about system layout these files or like the data. And the next question is about, so on the list layout, how to find an inode? I mean, given a request, how to get the inode from this kind of device. So let me give you, I think it's a long example based on a log structure file system where we're going to talk about how to get the inode based on this file system, because for each of the file system, they have their design concepts, so maybe different. But I'll just based on this log structure file system to give you some insights about how this kind of management works like. So first of all, we still need to come back to our challenge on the hard disk drive, because actually the data like file system is invented. Also, people are using the hard disk drive. So this is the reason why most of the designs that are related to the hard disk drive. Okay, so at that time, hard disk drive it should follow the disk rotation, this kind of access pattern. So it should be, I mean, if we are going to get the better performance from accessing hard disk drive, the sequential access is quite important. So actually, there is a subtle difference when we are talking about the sequential access. The scenario is like this. If we are going to write data in a sequential order on the hard disk drive, even it is a sequential order, but this is not enough. Okay, so the reason is about actually the plate on the hard disk drive rotates all the time when we power on the hard disk drive, right? So when we are saying like we are going to write the data on a sequential order, for example, I'm going to write like 3 files and in the sequential order, file 1, file 2, and file 3. But we didn't mention about the time, like we really write data inside, right? For example, if you write the first data and then you pause for like 5 minutes and you write the second data, and then you wait for another like 10 minutes and you write a third data. And you cannot make sure these 3 files, they are very close to each other on the plate because the plate moves over times, right? So we cannot control where is the precise locations for these data to be very close to each other on the hard disk drive. So this is the reason why the log structure file system counts. Because a better way is, or like I'm not going to say the better, I mean, one of the possible way is to issue a large number of contiguous writes. That means like this. That means we need to maintain a write buffer. So write buffer usually just like you need to partition part of the DRAM to for this kind of write buffer. So we first will buffer this kind of updates in the DRAM, and then we'll write in a batch to the hard disk drive at the same time. So with this manner, we can make sure this data, they can be continuous on the hard disk drive. So like this. If here are several kind of data here, like DJ0 to DJ3, okay? So DJ0 to DJ3, actually, they are all belonging to the same data called DJ, but it is so large, so there are 4 parts here, okay? So in this example, you can see for DJ is a file. So we give it an inode called inode j, right? And for inode j, there are 4 blocks belonging to this inode, block 0 to block 3. So block 0 means to give it some physical location here, okay? But the case is like this. Okay, one moment. Okay. So the case is like this. If we are going to write the data at the same time to the hard disk drive, we can make sure they are all in a sequential order, right? But if we consider another case, we first write DJ0 and then write DJ1, DJ2, and DJ3 one by one. But because one by one, we cannot make sure. For example, when this write buffer is going to write DJ0, DJ1, maybe DJ2, and maybe at the same time there's another process. It is also writing the different data on the disk, and at the same time maybe there will be interleaved with other process. For example, DJ0 after writing DJ0, maybe there is another data called DI from other process. Then DI0 will write near to DJ0. In this case, the data cannot be continuous on the hard disk drive. So having the data together in the right buffer and then write them at the same time to the hard disk drive is very important for the concept for the log structure file systems. And the root cause is because the disk plate rotates all the time. And also there are several processes that are working at the same time. So we cannot make sure if we write the data one by one to the systems, we cannot make sure they will be placed together, even they're in the sequential writing order. Okay. All right. So, okay. So when we write this kind of data structure on a hard disk drive, actually we say this is the reason why, if you still remember in the layout slides here, actually the boot block, super block, and inode table, actually they are all stored on the device. They are all stored on the storage device. And the reason is when one day you shut down your computers, actually those kind of files and information, they are all still maintained inside of the device. So if one day you power on the system again, then you are going to reconstruct the file system back. We can just read out the data from the disk, then we can reconstruct this kind of file system out. Okay, so same here. We write this kind of data and inode together into the hard disk drive, right? So in this case, we always need to find the inode before accessing the data because we don't know where is the data block until we can find the inode. Okay, and inode is just like a data structure, so there are several information inside. So the block location is one of the information. So for example, for inode J here, they comprise 4 blocks location here. They are from A0, A1, A2, and A3. A0, A1, and A2, and A3, and they are on the storage device. Okay. So actually, for another data means DK, because this is another file, so we have give it another inode code, so-called inode K. Okay. But here comes a question. I mean, how to find an inode in the disk? So for old Unix file systems, a very simple way is to organize in an array and place on disk at fixed location, right? If we have a fixed location for inode, then we can always start from a certain location and we can find it. Okay. So like this is an old Unix file system, for example, and here is the data, like D1 and then to a lot of data here, and then different data they're placed in the hard disk drive, and then we will reserve maybe, for example, the last amount of the space they are placed in the inode. So this is the first inode. Second inode means first inode will manage the first file. Second inode will manage the second files. So inode always store at a non-fixed locations, right? In this case, when we are going to access the inode, it is quite simple. For example, because inode is in the same size, so we only need to know the starting point for this inode structure. You can think about this inode table. It starts from A stars. So having this A star, we can directly get any inode in this area because they are in the same structure. So it's just like an array. So given an index with this starting point, you can always find the inode. So this is the simple way. Just like we just give it a set of amount. So for example, if we are going to get this kind of A inode, and it means like A star plus the inode index times the inode size, then we can get it. Okay, so this is one important thing is here. The inode size is a fixed size, right? The reason like we can do it like this is because the inode size is a fixed size. So this is the reason that I mentioned in last class is we will not put file name in inode structure because file name sometimes can be super large. It depends. I mean, you can make your inode file name super large, and the size will be hard to control. So in order to make the inode size to be in the same size, the file name was put in the dirty entry, not in the inode. Okay. Okay, but here comes a problem. Let's come back to the prior slides. Okay, if now the scenario is like this, if now we are going to take the benefit of the sequential access behavior of the hard disk drive. we should put the inode close to the data, right? Getting the inode, then we can get the data. So if we can put them on a very close tracks on the hard disk drive, then for example, the rotation count, then the disk head can read out the inode and the data at the same time. Then we can directly present the data to the user. That'll be super fast, right? So this is the reason in this slide we say moving them together from the write buffer to the hard disk drive is a good solution. But when we come back to the old Unix file system, the problem is they separate out the inode and the data, right? Because they are going to calculate where is the position of the inode, so they cannot mix the data and inode together. So it means at least we need two assets to get the data. First, we need to first get the inode, and definitely inode will not be in the close location with the data, right? Because data is super huge, and inode, if you have a lot of files, the inode table will be super large also. So you need to first get the inode first, and then get the data later. So you need to at least two disk access, right, to get the data out. Okay. So consider this scenario. If we are using this kind of log structure file systems, like here, actually we put the inode close to the data, or even we say we make the data and the inode they're stored contiguously. So in this scenario, after reading the inode DJ3, DJ2, DJ1, DJ0, they can be read out at the same time. So we only need get the disk head at this position, and because the disk will rotate all the time, so we can easily read out all the information we need to parse this file. We only need one disk access, then we can parse the data. Okay, so if it is possible to mix the inode and data together and then put the inode close to the data, then we can save at least half of the time, right? Because this one we need 2 times of the latency, and this we only need half of the performance to get the data. But the reason is, if in this case, then how to know where is the inode? Because inode and data, they are mixed together. Okay. So there is a way it's called the checkpoint region. So checkpoint region is a fixed and non-region on a disk. It contains pointers to the latest piece of the inode map. Okay, so the concept is like this. Actually, we still need a physical location to help us to locate where is the inode. Come to think about it, when we are talking about the patch table walking, we still need to get the very first table, right? We need to put the first patch table address at the CR3 register to start the patch table lookup. The same thing, we need some place to guide us where is the first to get the inode. So here are 2 concepts here. The first one is about the checkpoint region, and the second one is the inode map. So we are saying like, hey, actually, it is hard to record each inode one by one. So how about let's group it together. So for example, for inode map, the first inode map means we manage from the 0 to the J inodes. We make it in a group. So each inode map will locate a group of the inodes, a group of files. Okay. And then for each checkpoint region, we are going to maintain a group of the inode map. So for example, this one, checkpoint region will only point to the inode map. And parsing the inode map, we can get an inode. Okay, so inode map usually will be continuous with those data maintained in this inode. Okay, so we use this kind of indirections. We get to, we amortize the code. For example, if the file assets, they are belonging to the same inode map, then we can get a benefit, right? We can get a benefit about, we can just read the checkpoint region and then read the inode map. And because inode map groups like J files, so if the recent assets, they are related to these J files, then we can get a benefit here. Okay, so actually the time for accessing this, dog structure file system, the time will be between, sorry, one moment. Okay, the time will be between these two, because this is super slow and this is super fast. But for this one, we cannot find an inode easily. So a better way is to having an indirection. We group the inode together as an inode map. So in this example, if we use the inode map, then the latency might be between the slowest and the fastest. So this is the reason I say using this inode map, we can amortize it. Okay, but actually it's not enough. I mean, there is also a way for doing the optimization, but let's talk about it next time. So let's call it a day. Thank you guys.